Howdy folks, in this video we're going to look at some conceptual questions surrounding the derivative. There won't really be any computations here, but that doesn't make the problems easy. But let's see what we can do here. We'll just tackle this one problem at a time. The first thing we're asked to do is to give the domain of this function here in interval notation. So I think that this function, it's certainly defined at the value 1, and it's defined for all values up until I get to 3. So I could say that the domain would go from 1 to 3 with an open parenthesis on the 3, and then we'd pick that up and we'd go again from, and we'd pick up from 3, and we'd have, there's no domain value at 3, but just to the right of 3 we have domain values. Down here everything's good. It may look like initially that it's undefined at 7, but if we look up, yep, it is defined at 7, so we're doing from 3, we get to include 7, and just to the right of 7, and it looks like we have, for every x value along the x-axis, we have corresponding functional values. So I think that this goes from 3 to infinity for that part. So where then is this function continuous? Because we see that it's defined in a lot of locations, it's defined everywhere except for 3. Where would it be continuous? Well, it's certainly this function f. We're just looking at f right now. F is not going to be continuous at 3 because f isn't even defined at 3. But there are a few other places where f is not continuous. So let's see here. If we were to list the intervals for which f was continuous, I think we would do this from 1 to 3. Notice I put an open dot on the 1 here. Now, in this case, for this problem, if this had been my question, like that, then for continuity, I would include 1 because I'm saying that it would be left continuous at that endpoint. But that's not what I have in this case. So we're not continuous from the left here because the left-hand limit is 1, but the functional value is -1. And so we'll be continuous between 1 and 3, and then we'll be continuous again, it looks like to me, between 3 and 7, and again between 7 and infinity. Notice that although this function is defined at 7, it's not continuous at 7. Okay. The next thing we're asked to do is we're asked to find an a value so that f of a is equal to the limit as x approaches a. So this is the behavior at a point, and this is the behavior near. And so we want a place where the behavior at a point is the same as the behavior near. Hopefully you recognize that this is just the definition of continuity. What that means is I could take any x coordinate that lies within one of those intervals, and that will be sufficient. So I'm going to pick a equals 8, but you could have picked any number that was in the interval for which this function was continuous. So one way we could see that is if I were to compute f of 8 directly, looking at the graph, f of 8 we see would be 2, and if I were to compute the limit as x approaches 8 of f of x, meaning if I were to approach 8 from either direction, the corresponding y values appear to be approaching 2. Again, if we did that from either direction, approaching 8 from this way, that would give me this point on the graph, then this point on the graph, which corresponds to this y value, this y value. It seems to me as my x values approach 8, my y values are approaching 2. And so this is true. And so then we have, yep, sure indeed, f of a is equal to the limit as x approaches a if a is played by 8. So there's our answer to this question, a equals 8. Then we're asked to list all a values so that f is differentiable but not continuous. Well, this is a silly question. In order to be differentiable at a point, which means in order to be able to put a tangent line there, the function has to be continuous there. For example, around x equals 7, at x equals 7, we said the function wasn't continuous. It's impossible for me to put a tangent line on the graph of the function here. Go ahead and try it. I mean, who knows what that would mean to put a tangent line on the graph of this function here. There's no way to do that. And so if the function's not continuous, there's no way it's going to be differentiable. So we're going to say in this case that none exist. Here we're asked to list all the a values of the function f, where f is continuous but not differentiable. Now here this is a little bit different. Remember in class we saw that there were three ways in which a function could be continuous but not differentiable. One of those ways was if we had a corner at a point. At that point right there, we're not continuous because we've got a corner. The other way was if we had a cusp. So here we have a cusp at the value b, and so the function, even though it's continuous there, isn't differentiable. And then the third way was if we had a vertical tangent line. So if we had a graph that looked something like this, where we had a vertical tangent line at c. So here, again, it's impossible for me to put a tangent line at that point. Same thing down here. Who knows what that would mean to put a tangent line at that cusp? Okay. Here, I can put a tangent line, but the slope of that tangent line is undefined. And so it's kind of a different scenario from the other two. So anyway, we're looking back at our graph, and we're trying to find the points on the graph where the function is continuous but not differentiable. And I think in this case that there are two. I think that the two solutions are at a equals 2 and at a equals 5. So at 2, the graph has a vertical tangent line, so it's certainly not going to be differentiable. And at 5, notice that the derivative would be a negative value just before 5, and it would be exactly 0 after 5, but there's no way to go ahead and give the slope of the tangent line at 5. And so those are the two locations where the function is continuous, meaning they were points that were in this interval that we listed here, but we still couldn't compute the derivative. Okay? Notice we don't include 3 here in our answer because we've already said that the function isn't continuous at 3, so of course it's not going to be differentiable at 3. Moving on, folks. So the next thing we're going to do is one of the challenge problems here is in this blank graph, we're going to sketch the graph of f prime. So let me start off by doing a couple of things that I think are maybe a little bit easier to compute. If I were to come here on the graph of this function and I were to sketch a tangent line, notice I can observe what the slope of the tangent line is at that point. Same thing here if I were to put a tangent line or anywhere along this linear segment, I can compute the slope of the tangent line because the slope of the tangent line is just simply the slope of the blue line, and this blue line has a slope of 1. So between 7 and infinity, I'm going to have a slope of 1 for that derivative. So that will sketch a little better. I hope that makes sense. Now look between 5 and 7. Again, I could easily put slopes of tangent lines there, and the slopes of all those tangent lines are 0. So between x equals 5 and x equals 7, I'm going to have a derivative of 0. Now folks, we're not going to include the endpoint 7 for many reasons, but one of them is that the function isn't defined, well, let me just say it like this, the function is not continuous at 7, so we're not going to include 7. Here, though, we're also not going to include 5 on this endpoint, and it's not because the function wasn't continuous there. The function was continuous there, but it's still not differentiable, as we said in the problem below, that we had a corner at 5, and corners are points where we don't have differentiability. And the reason why is because the slopes of the tangent lines just to the left and just to the right are so abruptly different that it's impossible for the derivative to capture how the function is changing at that corner. So we're going to have that be an open dot. Here, if we were to sketch slopes of the tangent lines along here, these are all going to have what sign? Before we even decide what the number is, what sign is it? Well, everywhere along here, the slopes of the tangent lines are negative. And in fact, I think that the value of that would just be the slope of this line, which appears to me to be negative. So we go over 1, we go down 1, 2. It appears to be negative 2 to me, and that's going between 3 and 5. So between 3 and 5, we put negative 2. We don't include this endpoint because it's a corner, and we wouldn't include this endpoint either because there's this drastic shift in the graph. Okay? But it's not defined there, so it doesn't really matter. Okay, continuing on. We're now going to sketch the derivative between x equals 1 and x equals 3. And there's going to be something interesting that happens there. Okay? Notice that just a moment ago, we said that the function was not differentiable at 2. Let's see what's going on there. If I were to sketch some tangent lines along this, notice that close to x equals 1, my slopes of the tangent lines, they are positive, but they are shallow and positive, versus over here, where the tangent lines are still positive, but they are much more positive than they were over here. And in fact, if I were to bring these tangent lines getting closer and closer to x equals 1, the slopes of the tangent lines are approaching 0. So although this is not, the derivative is not defined at 1, just to the right of 1, the derivative is first of all close to 0, but slightly positive, and that's what I have here. Then as I move my x values to the right, if I were to sketch those slopes of the tangent lines, those become more positive, and we have that the graph would be taking off like this. Let me sketch that just a little bit nicer. I don't like the way that turned out. So there would be the graph of the tangent lines as we approach the x value 2. Okay. Notice that as we approach the x value 2, the slopes of the tangent lines become infinitely steep, arbitrarily steep, as steep as I want to make them until I get to the point where I have 2, and that's where I've got that vertical tangent line. So that's what we see here, that the derivative, the slopes of the tangent lines, are becoming more and more positive. So then just to the right of 2, notice I still have a very steep tangent line. So just to the right of 2, I have a very steep tangent line. And as I move closer and closer to 3, my tangent lines remain positive, which means the derivative, the value of f prime, needs to remain positive, but it's going to become less positive approaching 0 here. Okay. So what we have then is a graph that looks something like this in this case. And let's go ahead and just politely sketch for our reader the vertical asymptote that's in the derivative right here. Okay. So there's the graph of the derivative of this function. So folks, what I highly recommend is at this point you pause the video, and I would even erase your sketch right here that you've just drawn. And then I'd like you to try to redraw it using this graph to help you out. These are tough questions, folks, but they do get easier with practice. So pause the video, delete this sketch, and then try to redo it based on this picture. If you get stuck, you can just return to the video and see what was done. All right, let's scroll down here and let's look at these 6 remaining questions here. Folks, it's really important to me that you not confuse ordinary limits with the derivative or how to compute limits of derivatives. So we're putting all that information together here. This first question is asking me to compute the limit as x approaches 2 from the left of the function f of x. So folks, this is where we've got to be careful. And I'm going to go ahead and just for reading this, let me clean this up a little bit. Let me clean up some of my marks here. So the first question was, what's the limit as x approaches 2 from the left of f of x? So if we were to approach 2, that would give me that point on the graph, which would give me that y value. And if we get closer to 2, again approaching from the left, that would give me that point on the graph, which would give me that y value right there. And if we stepped even closer to 2, that would give me that point on the graph, which gives me that y value right there. I think that as x approaches 2, the y values approach 2 as well. So if we come down here, we're going to say that the limit as x approaches 2 from the left of this function was 2. Now folks, in this question we're also asked to compute a limit, in this case as x approaches 2, but here for the derivative function. So let's take a look at that. So if we could do this one of 2 different ways. I'm going to go on to my graph of the derivative function, and I'm going to approach 2 on my derivative function. That gave me that y value there. Let's approach 2 a little bit closer. That would give me this point on the graph, which would give me this y value right here. If I get even closer to 2, that's going to give me a point on the graph that's way off the, off the sketch portion of the graph, giving me a very, very positive y value. And it seems to me that on the graph of f prime of x, as x approaches 2 from the left, that my y values are approaching infinity. Folks, we could have also gotten that same information simply by looking at this function, and we would have found that as x approaches 2, the slopes of the tangent lines are becoming arbitrarily positive, and so we'd say that that derivative was infinity. Okay. Let's look at letter I here. We've got the limit of as x approaches 3 for the function f of x. So as we approach 3, let me clean this up again. As we approach 3 from either direction, did it have a direction? I forget. It didn't have a direction. So as we approach 3 from either direction, we see that the points on the graph have y values that are getting closer and closer to the y value of 3. So that means the limit as x approaches 3 of this function here is 3. Folks, these two problems, there's nothing new in these two questions. We've done them before, but what I'm trying to get you to do is do them also in context of some other problems with derivatives. Here we're asked to find the limit as x approaches 3 of f prime of x. So if we go over here, if we were to approach 3 from one direction, it would look like the limit was coming out to be 0. But if we were to approach 3 from the other direction, it would look like the limit was coming out to be -2. So in this case, the left-hand limit is 0, and the right-hand limit is -2. Those don't agree with each other, so this limit does not exist. That was tricky, folks. All right. These last two problems, I cannot overemphasize how much I think you should focus on these two problems. It's very important to me that when you look at these limit questions, you don't just see an ordinary limit. You see two special limits that we've been studying for quite a while. This expression right here is just the limit definition of the derivative. Notice it looks like your slope formula right here, y2 minus y1, all divided by x2 minus x1. So that's the slope of a secant line between 2 points on a curve. And then what we're going to do is we're going to take the limit as one of those points approaches the other. That is precisely what we mean when we say compute the derivative of the function f at 4. So once we recognize that, the problem's now easy. But until we recognize it, it looks like there's something complicated we're supposed to compute there. But this is just the limit definition of the derivative, or one of the two limit definitions. And so now that we've recognized that that's f prime of 4, we can go up and from one of two places. We can either go to 4 on our derivative graph and just read the value, in which case we get -2, or we can go to 4 on the graph, 4 on the original function and compute the slope of the tangent line there, and that slope of the tangent line is -2. But no matter how we do that, we get a derivative of -2 for that limit. Okay. So for letter L here, I want you to think about this one, and I'll give you a hint. This first problem used one version of the derivative, and so this was one of the limit definitions of the derivative at x equals 4. This is going to be something else. We had two versions of the derivative, and what is our x coordinate in this problem? So I'm going to let you try this one. If you're stuck, reach out to a friend as you're working through these pre-works. Just reach out and say, hey, what did you get for letter L? And see what they got. All right, folks, that was a long video. I appreciate your patience. The next two will be a little bit shorter. One thing I do want to point out to you is if you scroll down here, I've got you working on some more derivative problems. Here you can just click the hyperlinks to check your solutions, but please, folks, try to work the problem first without looking at your hyperlink solution. Then let me know if you have any questions, and I'll pick it up in the next video where we do a couple of challenging chain rule questions. Thanks for your patience.